All right, welcome to this week, lesson 6. We'll start by tackling problem number 1. It's about the Niemann-Pick disease. So for the Niemann-Pick disease, there's a dominant D allele for unaffected and a recessive D allele, and that is the affected Niemann-Pick disease. So our problem tells us that 1 out of 150,000 people have the Niemann-Pick disease, which means they have the little d, little d. I'm going to draw this a little bigger here. So our little d is 1 out of 150,000. The first question asks, what is the frequency of the little d allele in this population? If we remember from the Hardy-Weinberg equation, this little d is the same as the q squared part of the equation. So q squared equals this 1 out of 150,000, which equals 0.000067. So to solve for q, we'll just take the square root of both sides, and q will equal square root of 0.000067, which equals 0.0026. So the frequency of the little d allele is 0.0026. For B, it asks what the frequency of the capital D allele is. That's easy, it's just 1 minus little d, which equals 0.9974. What is the frequency of the capital D genotype in the population? So for that, capital D is the same as P squared in the Hardy-Weinberg. So we'll just take this, this number right here and square it. So 0.9974 squared, and that'll equal 0.9948. For D, it asks what is the frequency of the heterozygous genotype in the population? And that's our 2PQ part of the Hardy-Weinberg. So we'll just plug in our numbers here, 2 times 0.9974 times 0.0026, and that will equal 0.0052 for the frequency of the carriers for this disease. Problem number 2, we'll fill in a couple blanks here. So A says determine the Hardy-Weinberg equation that represents the frequency of the B allele. That'll just be the Q, little q, when we at these. So A is going to be Q. Well, the term in the Hardy-Weinberg equation that represents the frequency of the AB genotype, the heterozygous genotype, that'll be 2PQ, excuse me. For B, DeGeorge syndrome is an autosomal dominant disorder that affects 1 in 4,000 individuals. The 1 in 4,000 individuals in the population affected is represented by that'll be in this case, it's a dominant problem here. So it'll be both P squared and 2PQ. C, the question refers to the situation presented in part B. The number of individuals that are unaffected, they're represented by what's left over, the Q squared. D, the type of plumage found in mallard ducks has 3 alleles, MR, N, and MD. And the restricted phenotype, well, that's the order of dominance as well. The MR is first, then M, then MD. And it's asking which term in the Hardy-Weinberg equation best represents the frequency of the MD allele. Well, when we do an extended Hardy-Weinberg equation, we get P, Q, and then R will be our third term. So the answer for this one is R. And then E, This refers to the same situation in D. It says, what term in the Hardy-Weinberg equation represents the genotype of a duck with a restricted cleavage? That's the most dominant. So it'll be both P squared and then the other heterozygous options, 2PQ and 2PR.
So just to continue along with our little vocabulary in part F, the human disease blank is a result of an SNP, and that's going to be sickle cell anemia. Oops, spell that right. Part G, got some space here. Part G says blank is a term that describes a trait that produces a single phenotype in 99% or more of the population. That is going to be monomorphic. Question H, blank is another name for a local population. I don't know how you pronounce that. Or deems. That's how I've been saying it. And for the last little fill in the blank question, question I says blank. The blank genes in humans are highly polymorphic. And from your PowerPoint you're reading, that is going to be your MHC gene. So let's move into problem number 2. It tells us that Marfan syndrome is an autosomal dominant disorder. And so, question A asks us, what is the frequency of the non-disease allele in the human population? Well, that's what we're going to be looking for. And as Tanner has told us, this is going to be our Q squared term. And so 1 in 6,000 individuals are affected. That's going to be 1.667 times 10 to the minus 4th. And that's going to be our Q. We need to square root that to get the actual answer. So having done that, the non-disease allele is going to end up being 0.00008. And that is going to be our non-disease allele frequency. Question B asks us, what's the frequency of the Marfan syndrome allele in the human population? That we can, again, just subtract that from 1, power 0.00008, and that will give us 99992. And this is going to be the frequency. Oh, there's non-disease and there's the disease allele. So for part C, we're asked, what is the frequency of heterozygous individuals in the population? Well, a Hardy-Weinberg equation dictates that heterozygous individuals are going to be in 2PQ. So let's just do that. Plug in our P in this case. That's what that guy is. And this is our Q. Okay. So let's go 2. So there's one more. 8. 0.99992. Just plug that in your calculator and you're going to get 0.00016 or 0.016%. And those are going to be heterozygous. There's our answer for part C. Part D says out of a population of 5 million people, how many heterozygotes are expected? So we're going to take our answer, which is the frequency of the heterozygote from part C, and multiply that by, again, 5 million times 0.00016. And simple math in your calculator, you're going to have 800 expected heterozygotes. And that is going to be our answer for part D, and that will finish that off for us.
Problem 4. So there are three different genotypes that Jeffrey Minton and his colleagues found. There's the R2R2. There was 135 individuals there. Heterozygote R2R3 had 44, and R3 had 11. So the total turns out to be 190 individuals. First thing we need to do is determine the allele frequencies for each allele, for the R2 and the R3 allele. In order to do that, let's take a look at the homozygous R3. So homozygous R3, that's our Q squared, and that equals 11 out of 190 total individuals, which is 0.0579. So to figure out the allele frequency, we just take the square root of 0.0579, and we get 0.241. So that's the allele frequency for R3, was 0.241. The allele frequency for R2 then would just be 1 minus that number, which equals 0.759. Now this is what they ought to be at, but in part B, we're going to run a chi-square test to see if the observed genotypes actually follow the expected ratios that we just determined. So if we remember chi-squared, I'll clear this so we have a little bit more space. Actually, I'll leave these numbers up here because we'll need these. So chi-squared, that equals the observed minus the expected squared over the expected, the sum of that. So we'll do that for each of the genotypes. So I'll write over here our expected proportions again. So we have those. All right, so to figure out the expected amounts for each, let's start with the homozygous recessive, which will be Q squared. So that equals our, this is the Q value up here again, remember? So 0.241 squared, which equals 0.0579. And we'll multiply that by our total amount to figure out the expected amount of individuals. It turns out to be 11 individuals for the homozygous recessive. Our next is 2PQ, the heterozygotes. So that'll be 2 times 0.241 times 0.759, which equals 0.3658. So take that proportion and multiply it by the total individuals, 190. And that equals 69.5 individuals. That's the expected amount of heterozygote individuals. P squared, that equals 0.759 squared, which is 0.5761, is our proportion of heterozygous P's. So take that and multiply it by the total number of individuals. Find our expected individuals, which is 109.5. So now that we have the expected, and we're already given the observed, we can run the chi-squared equation for each one of these and add it all together to get our chi-squared value. So first one is Q, so that'll be 11 minus 11 squared over 11, that equals 0. Next one we'll do our heterozygotes. So that's 44 minus 69.5. squared over 69.5, and that equals 9.356. Finally, we have our p squared, which is 135 minus 109.5 squared over 109.5, and that equals 5.94. So we'll take the sum of all of these numbers, and that gets us a chi-squared value of 15.30. Part C will interpret this chi-squared value. So we have three different genotypes. So our degrees of freedom is n minus 1 or 3 minus 1. So degrees of freedom equals 2. So if we take a look at the chart on the PowerPoint from a couple lessons ago, we can see that for degrees of freedom of 2 and a chi-squared value of 15.30, that's well out of the expected range for chi-squared values. We want something below about 5.9, and we have all the way up to 15.3. That means that we will reject the null hypothesis under equilibrium, which means that evolution must be happening.
So the last problem that we're working on today, problem number 5, is talking about coat color in dogs controlled by 4 alleles in the population. So we have the C chinchilla, CD, which is a white dog with dark eyes, CB, which is the pale gray dog, and just plain C, which is the albino dog. Now, in kind of the given information, let's see. This is going to be an expanded Hardy-Weinberg equation, so we're going to have to include the, let's see, the P, Q, and the R. I won't write those up quite yet, but just know that this is an expanded Hardy-Weinberg equation. I said this meant P, we'll call it Q, we'll call it R, and then we'll do S. Whether or not that's right, I'm not sure. So question A is asking us, what's the frequency of the homozygous chinchilla, heterozygous pale gray with the albino genes? So let's just write these up. CCH, CCH. So that's one that we're looking for. The next one is going to be the pale gray. And then the last one is just going to be an albino dog. Okay. So pretty simple. Let me actually write up, we've been given these allele frequencies. This is 0.37. The black eye, or excuse me, the dark eyes was 0.23. The pale gray was 0.25, and the albino was 0.15. So let's just erase these guys so we don't get confused. Allele frequencies are listed up on top. And so for chinchilla, let's just multiply these guys, 0.37, 0.37. For the dark eyes, that's going to be 0.25. Because again, this is going to be a p squared value. This is going to be a 2pq. So we need to multiply that by 2, as well as the frequencies. And then over here in the bottom, this is going to be, what did we say, r or s squared. So that means we're just going to have to go 0.15 times 0.15. A little bit of number crunching your calculators. 0.1369 are going to be your homozygous chinchillas. They're going to be the frequency pale gray, albino, heterozygote, and then your homozygous albino is going to be 0.0225. So those are given frequencies. Part B is asking us, among a population of 2,000 dogs, how many would you expect to have the pale gray phenotype and yet be heterozygous? And in this case, we're going to use this exact same frequency because that's what we found The pale gray phenotype is the CB, and heterozygous, well, it can only be heterozygous with the albino gene. That's the only possible heterozygote. So we'll take that frequency times our 2,000 dogs in the population. And how many would you expect? Well, doing a little bit of math, that says we expect 150 dogs. Dogs. You spell the word dog, I promise. 150 are expected to be heterozygous with this particular genotype. So we'll write that CBC there. Part C is asking us, among a population of 5,000 dogs, how many would you expect to have the white coat with dark eyes phenotype and yet be heterozygous? So phenotype for the white coat, dark eyes, you have to have that C sub D, but that can be heterozygous with the pale gray or with the albino genes. We've got kind of a lot going on right now. We're going to end up going 2QR plus 2QS. Remember we called the pale the R and the albino the S. So 2 times the frequency of 0.23, that's for the dark eyes, multiplied by 0.25 for the pale gray. 2 times the same dark eyes frequency times the albino, that's our 0.15. A little bit of math, 0.115 plus 0.069 gives us a total of 0.184 for our frequency. And then we need to multiply by that by the population of 5,000 dogs to find out how many we expect with the dark eyes, white coat, but heterozygous. Again, a little bit of math in your calculator, 0.184 times 5,000 will give you 920 heterozygous dark eyes. Heterozygous dark eyes. Okay. Now, let's see, where do we go with this? I just solved that guy, and I'm going to erase him just for the sake of some board space. So we can do part D. Part He's asking us, among a population of 15,000 dogs, how many would you expect to have the chinchilla, pale gray, or the albino homozygous albino genotypes? Again, this is going to be 2PR in this case. That's what we called our pale. And this is just going to be 2s squared. So let's do that. 2 times 0.37 for our chinchilla. And for the pale gray, that's 0.25 plus, or means plus, if you remember that from a previous lesson. And then we're going to have 0.15, and that's the frequency for our chinchilla. It's going to be squared. 0.185 over here plus 0.0225 is going to give us a grand total of 0.2075 for our frequency. Now we need to multiply that by the population, in this case, 15,000 dogs, to get the expected value. And that is going to be 3,113 dogs. We had to round up in this case. So that's going to be the expected number of dogs with the given genotypes. So thanks for being with us for these lesson 6 problems, and we'll see you next time.